Hello everyone. Today I'm going to walk you through the concept of binary search trees and why they are so vital in optimizing search operation in data structures. I'll also explain how we can insert, delete, and search for elements within a binary search tree and why balancing a tree is crucial for maintaining efficiency. So if we see here, a binary search tree is a data structure where each node has at most two children referred to as left and right child. For any given node, all values in the left subtree is less than the node's value, and all values in the right subtree are greater. This property makes searching an operation very efficient with an average time complexity of O log n, where the tree is balanced. So I'll break them down by one by one. So the first one is inserting uh, the insertion operation. When inserting a new value, we compare it with the root. If it's a smaller one, we move to the left side. If it's a larger one, we move to the right side. This continues until we find an appropriate position. Next, we move on to the deletion, where deleting a node requires careful handling of three cases: deleting a leaf node, deleting a node with one child, and deleting a node with two child. So here, if you see the 8 is just a leaf node, so we were able to easily delete it. And moving on, we can see for the searching operation. Searching is a straightforward one, and where we repeatedly compare the target value with the current node and decide to move it left or right. So like if you want to search for 8, yeah, come from the root node 13. So since 8 is less than 13, we move left. And if we look at 7, 8 is more than 7. So we move a right side and we will be able to find the 8 number. So one critical thing to note is that binary search tree can become unbalanced, like leading to the worst case time complexity of ON. So like this, if it goes like a linked chain, it becomes unbalanced. So in order to maintain efficiency, techniques like AVL trees can be employed to keep the tree balanced. So we have a set of steps to go through, and the AVL tree is like a self-balancing binary search tree where the height difference between left and subtree are kept between -1 and 1. So let's look at here, since it goes beyond 1 plus 1, the tree is uh, moved to the left, and there'll be a balance brought. Just like how Thanos said, perfectly balanced as all things should be. So if you have to like summarize it, a binary search tree are a powerful tool for optimizing search operation. However, it's crucial to keep the trees balanced to maintain its efficiency. And balancing techniques like these aerial trees help in ensuring that our operation remain fast, even as the tree grows. So thank you for your attention. Do you guys have any questions?
Yes, Nirosh. Can you say how do we like specifically how we can handle the deletion of node with two children in the binary search tree?
Yeah, it's a good question, Iflal. Let me go to the slide. So if we see here, when deleting a node with two children, we need to find the node's in order predecessor. That's the largest value in the left subtree, or in order successor, the smallest value in the right subtree. So when we swap these value with the node to be deleted and remove that as whether it has a predecessor or successor. So this will ensure that the binary search tree property is maintained. Any other
Okay,
questions?
thank you.
Yeah. Yep.
Neeraj, I have one question.
Yeah, good.
What would happen if we didn't balance the tree and then continuously add the elements in the ascending order?
Yeah, it's a good question. So, Amjad, if we keep adding elements in ascending order without balancing, the tree degenerates into a linked list, and making the search, insertion or deletion operation take O in time complexity. So instead of O log n. So this is why balancing is important to maintain efficiency. See, just like this. This is a balanced one, this is unbalanced. Any else? Anything else?
No, Neeraj.
Okay.
Yeah, Nirvash, can you briefly explain how AVL trees help in balancing a BST?
Yeah, sure, Mokul. So if you see an avial tree is a self-balancing binary search tree where the height difference between the left and the right subtrees, so the which is what we call as the balance factor, should be kept between -1 and 1. So if an insertion or deletion causes this balance factor to exceed the limit, rotations are performed to restore the balance. So just like I mentioned earlier, so once the additions being going on, the number becomes +2, which is more than +1. So there'll be a rotation taking place to balance everything. So the same step follows on, and may the algorithm make sure that the number is maintained between +1 and -1.
Yeah, clear, Nirvash.
Any,
Understood.
okay. Anything else? Anybody else have any questions?
Okay, Nirosh, how does the choice of a pivot in rotations impact the performance of balancing in A-wheel trees?
Ah, it's a good question. So the choice of pivot in rotations directly affect the tree's balance. For instance, if the left subtree of the left child is heavy, we perform a right rotation. Whereas if the right subtree of the left child is heavy, left-right rotation is frequent. So the correct choice ensures minimal disruption to the tree structure, keeping the balance operation efficient. So that's it for today, and I hope everyone's clear about it. Are you guys clear?
Yes, Neeraj. Thank
Yes,
you for
Niraj.
your
Uh,
Yes, Nirosh,
yeah.
explanations.
thank you.
Okay. So to wrap up things, understanding and implementing a binary search tree is crucial for optimizing and searching operations in various applications, and balancing the tree using techniques like AVL, and even there's another technique called red flag trees, uh, will ensure that the operation remain efficient as even as the tree grows. So I hope this would have cleared everything about the binary search tree. And thank you for your attention. Hope this was an insightful session.